So let's now try to formulate this invariance condition mathematically. So the requirement that Lorentz transformations now preserve the relativistic space-time structure. So we want to capture mathematically the requirement that we preserve space-time and hence, in particular, causal structure. This requires, in particular, when we have in space-time two events, 1 and 2. And these two events are described in our frame F by 4 vectors. This is the 4 vector x curly underline 1, and this is the 4 vector x curly underline 2. And these two events have or have not a causal relationship. So we can draw, starting from event number 1, we can draw past and future cone. All events inside the cone have a causal relationship with one. Events outside the cone do not. Now we go to another frame. Let's say f primed. It has the origin at some different location, and the axes have a different orientation. And what we require is that the observer f prime sees the same causal relationship between 1 and 2 as the original observer f. What is the condition that there is a causal relationship between 1 and 2? That the event number 2 is in the past or future light cone of event 1. The condition for that is that c squared, and let's denote by c this maximum speed of information transfer. C squared times delta t squared, delta t, that's the time difference measured by observer f, minus the spatial distance, and here I use a straight underline to make clear that this is a 3 vector, the spatial distance squared. This is larger than 0. If this is the case, then event 2 lies in the past or future light cone of event 1. If, on the other hand, this is smaller than 0, then event 2 lies outside the past and future light cones of event 1. And if it is equal, then event 2 lies precisely on the boundary of the past or future light cone of event 1. For observer f prime, the criterion is the same, only that observer f prime, of course, observes a different time interval, delta t primed, and different spatial components, and therefore spatial distance, delta x primed with a straight underline. So observer f prime will say, well, these are causally related. If this is larger than 0, they are unrelated if it's smaller than 0, and it's just on the boundary if it's equal to 0. Our requirement is that f and f prime observe the same causal structure. Therefore, whenever observer F observes one of these three cases, then observer F prime must observe the same case. So the condition on the left-hand side, the respective condition must hold if and only if the respective condition also holds on the right-hand side for observer F prime. Let me try to indicate that here, that in the basis of F prime will measure a time difference delta t primed, which in general may be different from the time difference measured by observer F. But the requirement is that they still observe the same causal structure. You immediately see that in the limit of infinitely fast information transfer, so in the absence of a speed limit for information transfer, you recover the non-relativistic condition, and hence the requirement for the Galileo transformation, because in that case, in our condition here, the term involving, well, you can divide our condition by c squared, then you have delta t squared minus spatial distance squared divided by c squared. If c goes to infinity, then you can neglect the second part and you're just left with delta t, right? So this, you recover the condition delta t larger equal smaller 0 if and only if delta t prime larger equal or smaller 0. And hence, that's the preservation of non-relativistic causal structure. But the requirement for the Galileo transformation goes beyond that. Galileo, in fact, requires that delta t equals delta t primed. So hence not only the sign, but also the magnitude, the absolute value of delta t is equal in all reference frames. Relativistically, we do the same here. We make the same requirement here. We require not only that causal relationships are preserved in the sense that I wrote above, but more stringently, we also require that in fact c squared delta t squared minus delta spatial distance squared actually equals c squared delta t prime squared minus delta x prime squared. Well, this obviously contains the above condition as a consequence, but it goes beyond that. And this is the crucial invariance condition that will also lead to the mathematical form of the Lorentz transformation. So this requirement, this more stringent requirement, ensures that in the limit c going to infinity, we recover the invariance condition for the Galileo transformation. Yeah, of course, what's contained in this requirement is that this maximum speed of information transfer is the same in all reference frames. Let me denote this explicitly, that this maximum speed is the same in f prime, and in fact in all reference frames. And let me also denote that this requirement inside the box, which goes beyond the requirement above, ensures that we recover Galileo in the limit c going to infinity. Okay, let's see what this condition now entails for the form of the Lorentz transformation. Before doing so, I would like to introduce one additional notation here. I had introduced in the space-time diagram, I had introduced these basis vectors that correspond to the time axis, the ET. I would like to use this universal maximum speed of information transfer to rescale that basis vector and introduce a new basis vector E naught that is defined as 1 over this maximum speed times the basis vector ET that we had introduced previously. Correspondingly, the associated component, where we have a 4 vector that we write as a linear combination of our basis vectors, or 4 basis vectors, then in our original notation, the component associated with basis vector ET, that was time, t, but now associated with E naught, is a component x naught, which is related to time by c times t. And it has the unit of length. Then a 4 vector, so an x curly underline, has 4 components, which I denote by x mu. So this is short for x naught, which is ct, x1, x2, x3. This has the advantage that all 4 components now have the same unit of length, the same physical unit. And one usually introduces for the 4 vectors, for the components of 4 vectors, one introduces Greek indices as opposed to Latin indices. A Greek index always means this is a component of a 4 vector, and the value of that index goes from 0 to 3, versus a Latin index, for example I, which goes from 1 to 3, and therefore relates to the spatial components only. So Greek indices are space-time vectors, go from 0 to 3, and Latin are ordinary space, go from 1 to 3. Let me also introduce a 4 by 4 matrix, eta, with components alpha, beta. So alpha, beta are Greek, go from 0 to 3, and the components of that matrix are, on the diagonal you have 1, minus 1, minus 1, minus 1. Everything else is 0. Then the invariance condition that we had on the previous page can now be written in the following form. We have eta alpha beta delta x alpha delta x beta, where I omit, that's another convention that is typically applied, I omit the sum, of writing the sign for the sum, and use the so-called Einstein summation convention, which says that automatically identical upper and lower indices are to be summed over. So in this expression here we have in the eta, there's a lower index alpha, and attached to the delta, the first delta x, there's an upper index alpha. So we have an identical upper and lower index, and the summation convention says that then we have to sum over alpha automatically, and we don't have to write the sum sign. Back to the invariance condition, what we have written here is nothing but our c squared delta t squared minus the spatial delta x squared. Because we have the eta has only diagonal entries. So the first entry is eta 0, 0, that's plus 1. Delta x 0, that's ct. So we have eta 0, 0, which is 1. And then we have c squared delta t squared. And then the next non-zero entries of eta are all minus 1. So for example, we have eta 1, 1, that's minus 1. And then we have delta x1, and the same for the indices 2 and 3. So in total we have minus the spatial distance squared. So on the left-hand side, it's exactly the left-hand side in our invariance condition on the previous page. And this must be equal to the same eta alpha beta delta x prime alpha delta x prime beta. So this is another way of writing the invariance condition. Now we say, or we have a Lorentz transformation, and hence the delta x prime alpha, that is some linear combination of the delta, the unprimed delta x, so delta x beta, some linear combination of the delta x beta. You know, the basis vectors in the primed frame, they are some linear combination of the basis vectors in the unprimed frame, and correspondingly the components, hence the delta x's in the primed frame, are some linear combination of the delta x in the unprimed frame. And the transformation is effected by a matrix, capital lambda, with indices alpha and beta. And again, I use the summation convention. There's a lower beta and an upper beta, and this means that we have to sum over beta. So this in here, that's the Lorentz transformation. You can insert this into our invariance condition on the right-hand side, and you find that the matrix lambda, the transformation matrix lambda, must satisfy the condition lambda transpose times matrix eta times matrix lambda must equal matrix eta. And so the invariance condition, obviously this must hold for all delta x. Delta x is arbitrary. And then for delta x prime, you insert the transformation law with the transformation matrix lambda. And the invariance condition leads to this condition for the matrix lambda. So all transformation matrices lambda that satisfy this latter condition leads to a coordinate transformation that satisfies the invariance condition, and hence in particular preserves the relativistic causal structure. What does such a matrix lambda look like that satisfies this condition? To find a matrix that actually satisfies this condition, let me simplify the problem and focus on a special case. where I would like to suppress two of the three spatial dimensions. I would like to suppress the y and the z dimension, and I consider only one spatial dimension, namely the coordinate x. This means effectively that we are only consider the case where the observer f prime moves relative to the observer f in the x direction, and nothing interesting happens in the y and z direction. So f prime moves in x direction only. In that case, we can focus on a 2x2 submatrix of the full transformation matrix lambda, namely the entries lambda 0, 0, lambda 0, 1, lambda 1, 0, and lambda 1, 1, because these relate to the time component and the x component. Now, the condition said that the transpose of that matrix times eta times this matrix is equal to eta. Let me move this a little bit and write the transpose of this matrix, that is lambda 0, 0, lambda 1, 0, lambda 0, 1, lambda 1, 1. That's the transpose of lambda, multiplied with eta, which in this case, with two dimensions suppressed, is simply 1 minus 1, 0, 0. This must give eta, which is 1 minus 1, 0, 0. When you do the matrix multiplication, this gives three separate conditions, namely lambda 0, 0 squared minus lambda 1, 0 squared is equal to 1. Lambda 1, 1 squared minus lambda 0, 1 squared is equal to 1. And lambda 0, 0, lambda 0, 1 equals lambda 1, 1, lambda 1, 0. These conditions are satisfied if we make the ansatz that lambda 0, 0 and lambda 1, 1 are equal to the hyperbolic cosine of some quantity psi, whereas lambda 0, 1 and the lambda 1, 0 are minus the hyperbolic sign of the same quantity psi. You can quickly check the first and the second of these three conditions, then simply read cosine, hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. This is just the Pythagoras for the hyperbolic functions, so that's fine. And the third condition on the right just says hyperbolic cosine times hyperbolic sine equals hyperbolic cosine times hyperbolic sine. So that's satisfied. So this ansatz satisfies our three conditions. And it's in fact already the most general ansatz that you can make. You can convince yourself of that. We could also have satisfied these conditions if we had chosen, rather than the hyperbolic cosine, if we had chosen minus the hyperbolic cosine. However, the choice minus hyperbolic cosine, we exclude because we want to, in our Lorentz transformation, also our set of Lorentz transformations, we want to include as a special case the unit transformation, where we don't change anything. We stay in the same reference frame. So the transformation matrix lambda is the unit matrix. So this must be contained as a special case. We have the unit matrix if we choose psi equal to 0, because then the hyperbolic cosine is equal to 1, and the hyperbolic sine is equal to 0. So with this choice, we include the special case of a unit transformation. If we had chosen minus hyperbolic cosine, then we would have lost this special case. Yeah? So let me just write it, which we exclude the minus sign because we want to include the special case lambda equal to the unit matrix. So, in other words, in this special case where we suppress 2 of the 3 spatial dimensions, a general Lorentz transformation has the form hyperbolic cosine of psi, hyperbolic cosine of psi, and minus hyperbolic cosine of psi, minus hyperbolic sine, minus hyperbolic sine of psi, where the parameter psi is called rapidity. And we have yet to understand how rapidity is related to the ordinary velocity with which observer f prime moves relative to observer f. This is something that we are going to look at very soon, how these two are related. One aspect that you see immediately that is new in relativity, that you don't have in the non-relativistic case, is that this Lorentz transformation mixes spatial and time components. And what we do have non-relativistically is that a new spatial coordinate is a function of the original space coordinates, and then also some contribution proportional to time. Yeah, so you do have the effect non-relativistically that time enters into the transformation of a spatial component, a spatial coordinate, but never the other way around. Non-relativistically, t prime can differ from t at most by an additive constant, but the transformation of time is never affected by a spatial component, never enters into the transformation of time. But here you already see from this form of the Lorentz transformation that t prime depends on x. Depends not just on t, but it also depends on x. So it mixes space and time coordinates. Before I come back to the issue of rapidity, let me consider how the basis vectors in space-time transform. And what we've looked at now is the transformation of components of 4 vectors. Next, I would like to consider the transformation of basis vectors. So in other words, of the 4 bases, the basis in space-time. Let's say we have 2 events in space-time, and the distance vector between these 2 events, that's a 4 vector, and the distance vector is delta x curly underline. So it's a 4 vector that describes the distance in space-time between 2 events. That can be written either in the basis of observer f, then we would have components delta x mu and basis vectors e mu, or it can be written in the basis of observer f prime. Then we have components delta x prime mu and basis vectors e mu primed. Now we know how the components transform. That's what we had just looked at. They transform with this transformation matrix lambda. At the same time, we must have this equality here. And this tells us immediately how the basis vectors must transform. So we know that delta x prime mu, that this is lambda mu nu delta x nu. When we insert this here, then we find a transformation law for the basis vectors. And then we find that E nu must be lambda mu nu E prime mu, which is lambda transpose nu mu. And when we solve that for the primed basis, then we find that in a compact notation that E 0 primed, basis vector E1 primed, E2 primed, E3 primed, that this is equal to lambda inverse transpose. So this matrix acting on the unprimed basis vectors E0, E1, E2, E3. In the special case with two spatial dimensions suppressed, we find that basis vector E0 primed and E1 primed, that this is equal to hyperbolic cosine of psi, and now in the diagonal, and now in the off diagonal a plus hyperbolic sine, acting on E0, E1, the unprimed basis. So let's try to draw that. Let's say we have in the unprimed basis, observer f has basis vectors E0 and E1. Now let's say psi is positive and it is strictly larger than 0. Then the hyperbolic cosine of psi is strictly larger than 1. And the hyperbolic sine of psi is larger than 0. So this equation tells us that E0 primed lies somewhere here, where if this, let's say, is 1 unit, then this here is the hyperbolic cosine of psi, which is larger than 1. And this here is the hyperbolic sine of psi. This is what the equation tells us for the basis vector. It's hyperbolic cosine of psi times E0 plus hyperbolic sine of psi times E1. Again, if we say this has E1 is 1 unit. What about E1 primed? It's E1 primed is hyperbolic cosine of psi times E1. So this here, this length here, that's again the hyperbolic cosine of psi. And this length here is the hyperbolic sine of psi. So this is what the new basis looks like. Both the basis vector E0 prime is tilted and also E1 primed is tilted with respect to the basis vectors in the original frame.